To us about birds and climate change. Rob, please take the stage.
Well, this has been fixed up. Just to say that for Catherine Tyrrell's prize-winning work now on the diet of the pied flycatcher in Wales, there's a poster up on the balcony there. And Catherine's work used a technique that's been developed at Cardiff, extracting DNA from the poo of pied flycatchers, and some of that DNA belongs to the bird's prey, and then you can work out from the sequences of DNA what that prey comes from. So Catherine's work is on display up at the top there.
Luckily they don't have to do that with us.
I feel like I'm going to do a TED talk. Hang on, here we are. Okay. Great, well, I'm going to talk about work going on at Cardiff University about the responses of birds to climate change, and focusing on the behavioural studies. All right. Is that can everybody hear? Okay, so at Cardiff University we have an animal behaviour research group, and we're focusing on what can studies of animal behaviour tell us about how birds and migratory birds in behaviour are being affected by and responding to climate change. And climate change, of course, is one of the greatest ecological challenges of our time, and so it's useful for us as a group to think, well, what can we as Welsh ornithologists contribute? And my one-time project supervisor, Nick Davis, would say, being a champion of behavioural studies, that behaviour can give us a better understanding of how organisms, including birds, can adapt in various ways to a rapidly changing world. And so down at Cardiff, we've got a group of people investigating behavioural responses to changing climates, and in particular the mechanisms of behaviour that might mediate the responses to climate of individual birds, the bird populations, and that of course leading to changes at the species level, both in terms of population, but also the way in which that species behaves, and whether that species will survive and thrive or become endangered and possibly even reach extinction. So in the talk today I'm going to focus on migratory birds, and choosing the migratory species because of course migration is one of the major challenges to survival faced by many birds over the course of their annual cycle. So every year about 5 billion individual birds of about 200 species, depending on whether you think Iberian jiffchaff is a species or not, are pouring south from Europe, crossing the Mediterranean and the Sahara ecological barriers to spend the winter in sub-Saharan Africa. And of course many of them are going right down to the south, so Rich Facey's swallows breeding in Cardiff Riding School are spending the winter. I think he had one run over by a car in Orange Free State, didn't you, Rich? Wasn't actually Rich's fault. So we might expect some severe impacts of climate change on these birds because they are obviously depending on several or many different locations over the course of their annual cycle, and these locations of importance are scattered across the globe. And so it doesn't just matter what's happening at any individual site. All of these sites are important for that population to survive the annual cycle. And so these are birds that are vulnerable to the sum of all impacts across a global scale, and so we might expect them to be particularly affected by climate change wherever that climate change is of is having an impact. And although we tend to talk about conservation of individuals and species, populations, as a behavioural biologist, I also think that there can be behaviours that we might want to conserve. And to me, migratory behaviour is one of those almost miraculous phenomena in the natural world. And as well as conserving species of songbird, I'd be very keen to promote the idea of conserving migratory behaviour as an important phenomenon that brings a lot of cultural value and ecological value to us. So how might migration strategies respond to climate change? And well, one way in which migration strategies can respond is by evolving new strategies. And you might think, well, evolution happens on a timescale of millions of years, but actually there are several examples, not least from the black cap here, of migratory strategies that have evolved, changed over much, much shorter timescales. And classic study by a group of German biologists focused on black caps that breed in central Germany, and their traditional wintering areas are in Spain and Portugal. Some of them are crossing into North Africa, some of them are even crossing the Sahara as well. So in the autumn, these black caps are migrating southwest, but in the 60s and 70s, a new migration strategy arose. It was actually subsequently been shown to have a genetic basis, so it's a mutation that has led these black caps in the autumn not to migrate southwest, but to migrate west. And so, as we all know, we've had black caps wintering in the UK for several decades now. These are actually birds mainly originating in the central German breeding areas. And this genetic mutation spread from 0% through the population and reached over 10% in just 30 years. So this is a selection-driven increase in a new novel migration strategy operating over a decadal timescale. And the Centre for Wintering Black Caps in the UK at first was Western-super-Mare. Nobody's quite sure what it was about Western-super-Mare, but potentially, a high density of bird feeders combined with ameliorating winter temperatures, warmer winter temperatures over the last few decades, has enabled the black caps that do winter in the UK to have quite high survival. Being relatively local winterers, they're able to get back earlier to the German breeding territories and hold the best territories. So those birds wintering in Western-super-Mare and other places are available, they have a higher breeding success. And so this in turn promotes the spreading of this new migration strategy. So although we think of evolution as occurring over millions of years, actually black caps can or have responded in an evolutionary way over just 30 years. And we shouldn't forget either that it's only about 10,000 years since the Sahara actually became an ecological barrier that birds had to do a single flight across. During the previous glaciations, there were these mega lakes and open wooded savanna in the Sahara region, and birds would be able to spread in much shorter migration flights down through North Africa into West Africa. So evolutionary changes are possible. We've got the kind of super example of black caps changing over timescales of decades. Our migrant songbirds that we think of as Welsh migrant songbirds, of course, they're actually African songbirds that we're borrowing for the breeding season. They've been doing this trans-Sahara flight for the last 10,000 years or so. But there are plenty of examples, of course, where evolution is slow. So the question is, can these evolutionary changes be quick enough for birds to survive and track the rapidly changing conditions that we're already experiencing? and the conditions that are only likely to accelerate over current decades. So when we're thinking about migration, of course, migration is a behaviour, and there's an important sense in which migration strategies don't have to evolve because birds can decide in an instant to change their behaviour. So this behavioural flexibility in migration strategies can also be very important in understanding how birds are able to respond instantly to rapid environmental changes, for example, from one year to the next. And of course, our migratory birds are having very mixed fortunes. So the flycatchers that Catherine and Jess Smith and others are studying in mid-Wales are examples of these populations of trans-Saharan migrants that are rapidly declining. Other species, wheatear and sedge warbler, they have regular ups and downs, and sedge warblers come into the story a little bit later on as to why that is. But some species, like the reed warbler here, have shown quite consistent increases coinciding with recent climate warming. So how can we understand how these populations are changing in very, very different ways? And part of the answer relates to the behavioural mechanisms by which birds respond to their current conditions. So that's what people down at Cardiff are getting up to. Various people come into the story now. So Renata Medeiros studies stormy petrels. Adam Seward was, we popped him in a jiffy bag and sent him up to Shetland for 3 years. This is the kind of fieldwork transport that Cardiff research grants can fund these days. And he was studying wheatears. The newly married Rich Facey, congratulations to Rich on adding a double barrel the last couple of weeks, studies the swallows at Cardiff Riding School. And then we've got James Mafidis, Sarah Davis now studying reed warblers in Cardiff Bay, and then Jez Smith, the wild man of the Welsh woodlands around Llustina. So let's have some case studies of behavioural studies where we're looking at the responses of birds to rapidly changing environments. So the first of these is the storm petrel, the smallest of the Atlantic seabirds. So they're about the size and weight of 2 one-pound coins or one house sparrow, and they're tiny little birds, but they're highly oceanic. They're spending most of their lives out at sea. They come on shore to breed, of course, but they're every year doing these massive migratory journeys, and for a house sparrow-sized bird on the open ocean, this is an incredible thing to be doing. So they're breeding around the western seaboard of the Atlantic. Skocum in particular has a big colony, of course, a few on Bardsey and elsewhere. And these birds are coming south then, around the bulge of Africa, and many of them, at least, are wintering in the upwelling fertile waters of South Africa and Namibia. Some of them, from BTO ringing records, are rounding the Cape and even getting, just into the Indian Ocean. So it's astonishing global travel, but they are very good at doing this. They're regularly surviving into their 20s. There are plenty of storm petrels that are into their 30s as well. So there are several storm petrels who are older than several of you, for example. So we're studying them in Portugal, because it's on the migration route, as well as a lovely place to study storm petrels. We're collaborating with Mark Bolton, the RSPB crowd on Shetland, and of course we're collaborating with Rich Brown, Giselle Eagle, and their crew on Skocum Island. And these birds can be captured during their migration. It's quite unusual to be able to study study seabirds of any sort away from the colonies, but it turns out that storm petrels are attracted to their song even a long way south from their breeding range. So you can sit on the cliffs of Portugal. This picture is actually on Skocum, but you can take your kit to the cliffs of Portugal, people like Heather Coates have done this over many years. And you can play this little bubbling song to attract storm petrels into a mist net on the cliff. And storm petrel's song, I don't know if you've heard it, but it's supposed to sound like a fairy being sick. I don't know if you've heard a fairy being sick, but I don't have a recording here, but I can do an impression. It sounds a bit like... There we go. And so you can do this all night, not yourself, you can play it on a speaker and the birds fly around and you can catch them then in a mist net. And this is the kind of result that we've been getting in Portugal. It's a long-term data set these days from 1990 onwards. And what I've plotted here is the body weight of these birds. Every year we manage to catch 100 or more. 100 is kind of what we're aiming for. Often we get more than that. And you can see that their body weight is actually changing a lot in this sort of fluctuating way from year to year. So these birds are sort of lean mass around 25 grams, but their amplitude of this fluctuation is more than 10% of that. So these represent very big changes in the level of stored energy reserves, mainly as fat reserves, that the birds are carrying on migration. And one of our research questions over the recent years has been what drives these big changes in what is essentially the birds' migration fueling strategy. So they're changing how much energy they're carrying during their migration. So one kind of explanation can be changes in the environment between years. So on this graph I've plotted the temperature of the sea off Portugal, and each dot here is the average body weight of storm petrels in each of those years since 1990, relative to their average body weight over the whole period. So in years when the sea temperature is relatively warm, storm petrels are relatively skinny. In years when the sea is relatively cold, storm petrels are carrying these big fat reserves on migration. But an important part of this result is that there's a very strong time lag in that relationship between sea surface temperature and body mass. And it's actually sea temperatures in April, at the end of the winter, start of the spring, that are most strongly linked to storm petrel fat reserves when we catch them rather later in the year, in May and June. So rather than being a direct thermal response to the environment, storm petrels aren't putting on extra fat as a sort of overcoat to keep warm if the sea is chilly. Instead, it seems to be some less direct mechanism. And one of the primary explanations is that that link, that time-lagged link, is via the effect of climate on the bird's food supply, and food supply then affecting what the birds are doing with their energy reserves. So this is where Renata Medeiros and one of the academic staff, Bill Simonson down at Cardiff, came in. Renata's PhD was primarily focused on trying to find out what storm petrels actually eat on migration, because of course they're very difficult to study away from the breeding colony. So this is the same technique that Catherine Wan, I don't know if I mentioned her award-winning poster up on the balcony there, but it's essentially taking DNA from the feces of birds, storm petrels in this case, and then amplifying it up, increasing the number of replicates of that DNA, and then working out what that DNA came from. And there's various ways to do this. These days, people are using something called pyrosequencing, which is able to give literally thousands of DNA sequences from a single fecal pellet. And those sequences can be identified because there's a lot of work being done on sort of barcoding lots of species in the sea and terrestrial environments so that they can be identified in this way. So this actually allows people like Renata, I have no idea what goes on in this lab work, I should point out. This is what the lab people are able to do, though, is provide species-level descriptions of diet and foraging behaviour of the birds in these different years. So what do storm petrels eat on migration? Well, when they're passing Portugal, this DNA analysis reveals that they eat a lot of sardines, as do I when I'm passing Portugal, to be honest. They eat a lot of mackerel species. And this is to be expected. These are the really abundant small pelagics, the small fish at the sea surface offshore. But there are also some nice surprises. So there are quite a lot of deep sea species. And if you know storm petrels are dipping, of course, into the surface waters, they don't dive beyond a few centimetres, really. But these are species from the depths, and these are probably being accessed by the petrels as fishery discards. So they're being trawled up, processed, and bits of fish flesh and small fish are being discarded, and these are ending up in the storm petrel diet. Storm petrels also turn out to eat a lot of terrestrial invertebrates. You think, why is there butterfly DNA in storm petrel poo? Well, if you bob around on small boats off the Portuguese coast, you actually see loads of butterflies. They're crossing the sea. Some of them are migrants, some of them are just blown offshore, and butterflies are often getting stuck to the sea surface, and storm petrels are picking these up, evidently. We've also found storm petrels that have eaten dolphins. Now, they haven't necessarily eaten the whole dolphins. I like dolphins, but I couldn't eat a whole one myself. And how does this DNA get into storm petrels? It was probably from scraps of flesh, or they could be eating fragments of storm petrel feces. And so there's various routes by which this can end up in the diet. And they're also eating lots of crustaceans, zooplankton, all sorts of things. Some of these are actually become active in the surf zone, so along the beach, only at night. And so this is a clue that actually Portuguese, while they're passing Portugal, storm petrels are foraging along the beach at night. We were always assuming they were way offshore. So it's a very mixed diet, very big proportion, about half the DNA sequences come from sardine. So this allows us then to make the links between climate, so sea surface temperature is the kind of oceanographic representation of climate. Sea surface temperature that subsequently affects the primary productivity, so the phytoplankton in the sea, and then the phytoplankton, is sustaining a whole suite of species of zooplankton, those little isopods, and that in turn is feeding the small pelagics, the sardines, the mackerel, and so on. There's also something called the North Atlantic Oscillation. This is a El Nino-style ocean basin scale climate fluctuation, a bit like El Nino but on a smaller scale and in the North Atlantic. And this also is affecting productivity, which has implications for the food chain, ultimately affecting the bird's body reserves. So what this is all suggesting is that these extra fat reserves that stormies are carrying on migration are a kind of strategic buffer. When food is scarce, the birds are heavier, so they're building up extra fat reserves in years when food is scarce and their starvation risk is high. So if they do find a food patch, they forage intensively on that and build up a bit of fat reserves. In years when food is abundant, they're less bothered about starvation, so they stay lean and mean, they're more flight efficient, and they're able to avoid carrying this burdensome extra body weight. And they're also switching their prey between years, so sardine stocks vary a lot between years as well, and so in years when sardines are abundant, then they form a bigger part of the bird's diet. So let's have a different case study now. This is a case study from wetland birds. James Affidis talked in some detail about his studies at this conference last year. So I'll give a little update on some of his results, and then we'll move on from that case study. But James's species of interests include Chetty's warbler, of course a resident, but a bird that has increased massively over recent decades. Reed warblers, which are increasing, and sedge warblers, which show these repeated fluctuations. And so part of James's questions are, what are the links between climate? Are there any links between climate and these population changes? And how does behaviour mediate these population level fluctuations? So these are the kinds of questions that James uses to make the link between climate and bird populations. So first of all, how does temperature and other aspects of climate like rainfall affect bird food abundance? And these are studies on invertebrates and the growth of the Phragmites reeds that these invertebrates depend on. And it's not just the overall abundance of invertebrates as bird food, but phenology, the timing of availability of the food, is also an important part of this sort of question. So how does climate affect food? And how does food availability affect all sorts of behavioural aspects that can feed through to survival? And recruitment is the ability to produce chicks to join the next generation, essentially. So here are some results looking at the impact or the link between climate and bird food supply in the form of invertebrate abundance. So what we've got here is 3 years worth of results from Cardiff Bay, where James and I would trog around with our little yellow sticky traps, catching invertebrates each week. And here we have the number of invertebrates per sticky trap against week of the year for 3 different years. And you can see that there is big seasonal variation, as you might expect, in how much bird food there is, invertebrate food. But also, there are big differences between years in how broad that peak is, how sharp it is, and how long the peak lasts, and when the peak occurs. So around those seasonal patterns, there's a lot of variation, and that variation in number of individuals can itself be very closely tied to temperature. So if temperature goes up, then the abundance of invertebrates in general goes up, including some of the key prey species, particularly for the wetland birds, the chironomid midges. I can confirm there's a lot of chironomid midges in Cardiff Bay. And other aspects of climate, rain and wind, have measurable effects as well on the abundance of bird food, but also the timing of when that abundance occurs in the year. So James measured that with observational studies, just sticky trapping week by week, but he also manipulated temperature using mesocosms, or greenhouses as I like to call them. And so this is in the grounds of Dow Corning, the huge chemical works near Barry. These are some of James's enclosures. Phragmites reed blocks with increased temperature caused by these canopies. And we realised that this is an experiment visible from space. This is Google Earth looking down, happened to be taken just as James was setting up his mesocosms in the back garden of Dow Corning there. So these are some results from that experiment. So this is the abundance of bird food against the week of the study into the spring. And you can see here that when experimentally warmed, the reeds produce more invertebrates in total, and the peak occurs earlier in the year than under ambient conditions, just normal weather conditions. So these are measurable impacts of climate on the timing and abundance of bird food. We also went to Cardiff Bay, put James in a very large pair of waders and got him to dig up bits of reed bed, which we then brought into constant temperature rooms in the university, and we had these mini reed beds in rooms of different temperature. And here are some of those results. So maybe a little bit hard to see these colours on the screen, but as temperature warms down the page, the peak is shifting earlier and earlier in the spring. So warming has a very measurable and rather strong effect, particularly on the timing of bird food. So what's the link between bird food and bird behaviour and bird survival and bird populations? Well, part of that link is the diet. And again, it's Catherine and Renata's technique, now being taken up for a PhD on the warbler diet by Sarah Davis, Cardiff native. And here we have some initial results from that sort of study. We've got CWs, chetties, reed and sedge warblers for different taxonomic groups down the page. And you can see that there are quite big differences between these very, very similar little brown birds in what they're eating. So sedge warblers are really focused on chironomids. About 70% of the diet is chironomids. Reed warblers, about a quarter of the diet. And reed warblers are generalists, eating quite a lot of everything. Sedge warblers really are specialists. And so these different diets might explain partly the different responses of these populations to climate. So James and I over the years have done various food supplementations, sort of saying if climate increases food supply, what would the effect be on bird behaviour and survival? Well, let's find that out by giving birds lots of extra food in the form of mealworms. And here we see little reed warbler. This is in Portugal, which we've trained to collect mealworms from on top of an electronic balance. And this is a setup. You video the bird hopping on and off the balance over a series of days, and you get these very nice weight trajectories. And this is our setup. We've got the video recording the balance. This is our Millennium Stadium style sliding roof. And this goes on over the breeding season. So these are some of the results, and increasing food supply has measurable impacts on all sorts of behaviours. For example, when do reed warblers lay their eggs? So 0 here is the average egg-laying date of the Cardiff Bay population. And in a warm year, having extra food caused a big shift in laying date. Okay, but in cold years, there was no effect of that extra food. And what's going on there is because reed warblers need reeds to build their nests and lay their eggs, it's only in the warm year that the reed growth is accelerated by temperature, so they can actually lay their eggs earlier if they've got more food. In the colder years, these 2 years with much lower spring temperatures, reed growth was too late for them to take advantage of this extra food, so they couldn't move their egg-laying date forward. So it's a nice interaction between the effect of food supply and climate conditions. There was also some quite surprising other changes caused by extra food. This is the total duration of the incubation period. And these fed birds had substantially shorter, about 10% shorter, incubation periods, which wasn't an effect that we were expecting, but the explanation seems to be that if they've got extra food in their territory, they can leave the nest relatively quickly, do lots of foraging and get back to the nest in order to continue their incubation. So the total incubation period is accelerated. These fed birds also had a much higher nest survival, and that's partly because they're incubating for a shorter period, so there's less time available for the nest to be predated, but also they spend more time nearer the nest and they're more active in the defence of the nest if they're receiving more food. So these are unexpected effects of what changes in behaviour we see around the breeding cycle if climate increases food supply, and we simulated that using mealworms. Some other results are much more intuitive. So food supply has a big impact on chick growth. So unfed chicks get bigger, that's not a surprise, but fed chicks get bigger, quicker, and end up heavier. And this has a measurable impact as well on survival after they leave the nest. So the total impact then on breeding productivity, how many chicks can reed warblers produce from their first brood, giving birds supplementary food increases their total productivity of chicks in all of the years, even though only in the warmer year were birds able to move their egg-laying date forwards. But it's not just breeding, of course, that impacts the population. Reed warblers have got to do their migration, overwinter survival, and get back to Cardiff Bay to breed. And just like the storm petrels, birds are using fat as fuel for their migration. Here we can see a reed warbler. Its head is behind my fingers there. I'm blowing gently on the bird's belly, as you do, and parting the feathers. You can see these big blobs of fat overlying the more purple muscle below. And these are literally the energy reserves that the birds will burn up, use up, during their migration journey. So we can, again, use the trick of weighing birds remotely at feeders to look at what's their lean body mass. For a reed warbler, about 9 grams, so there's almost nothing to these birds. And normally, reed warblers put on a few grams of fat and typically then set off on their initial migration flight at about 13 grams. Okay? So that's with natural food availability. With supplementary food, in fact an unlimited supply of mealworms, reed warblers go a little bit crazy. And these are body mass trajectories of individual reed warblers. So this is one bird with joining the dots is one bird. So here's another bird and another bird. So this bird set off on its migration at over 21 grams. And this is a lean body mass bird of 9 grams. So more than half of its body mass was a blob of fat. And as these birds up here are really at the aerodynamic limits for a small flying bird. So you let them go after weighing them, if you catch them to ring them, and they do a kind of shallow dive and just about get out of over the nearby bushes. So you know, they are as fat as it's possible for a 9-gram bird to be and still fly. Whereas unsupplemented reed warblers doing something very, very different. So this is a real dramatic shift in the fueling strategy that's caused only by a change in the food supply. That's the only difference in these birds' lives. So what's the implications for that massive switch? Well, more food allows faster fueling, but in particular it allows them to leave at a much higher body weight. And we can use flight range simulations to estimate what their migration strategy would then be. So under natural food conditions, birds are getting to about 13 grams. They're doing these short hops down through Europe till they get to Iberia, where they get substantially heavier for the Mediterranean and Sahara crossing. In years when, or in circumstances where food is super abundant, where they've got a mealworm feeder in their territory, the reed warblers are switching to doubling their body weight, and this is enough stored fat reserves for them to make a single direct flight to West Africa. That's not to say that they then do that, but if they did stop en route, they wouldn't have to eat anything more because they've already got that energy stored. So it's a dramatic change in how much they're relying on stopover sites along that route. So fewer and shorter stopovers needed, but potentially do the whole journey much quicker because refueling and feeding takes several days, and potentially they can go further as well. And you think, well, that's crazy behaviour for a reed warbler to do that, but of course this is exactly what sedge warblers with their specialist diet are doing every year under natural conditions. Because reed warblers specialise on the plum reed aphid, which blooms super abundant in reed beds in the autumn, and these are able to, in the normal circumstances, double their body weight and fly direct to West Africa. So actually, although we're enormously surprised to find reed warblers doing this, it's actually a strategy that's being used all the time by sedge warblers. So in other words, if climate changes food supply, specifically increases food, we'd expect food supplies to affect fueling decisions, migration timing, and abundance of migrants. And of course, these are the changes that we are actually seeing in the real world, these changes over recent decades. So, the reed warblers is an important case study, and James Vafidis has really pioneered this sort of approach. But we've also had studies going on with Adam Seward on wheatears. Jess Smith is doing this at the moment with pied flycatchers. And these are birds spending the winter in sub-Saharan Africa, of course. And it's been well known for many years. Some classic BTO research here is the link between overwinter survival in species like sedge warblers and sand martins and rainfall in the Sahel zone, southern Saharan fringe in Africa. So in years when the Sahel is wet, sedge warblers have an over 50% likelihood of surviving the winter and coming back to breed. If there's drought in the Sahel, that overwinter survival is almost zero. So it's a massive impact on overwinter survival, depending on how much rain there's been and how flush the wetlands are, basically. Sedge warblers and sand martins are feeding in these wetlands. For reed warblers, there is a relationship between survival and rainfall in the Sahel, but there's lots of variability around that, so it's a much weaker relationship. So why should this be? Well, we felt it was important to go to Senegal to check. So this is Jez in Senegal, and we were looking at the habitats where reed warblers spend the winter. And it turns out, although we think of reed warblers as wetland birds, they actually have two quite distinct wintering habitats. So some of the population is in wetlands, purple heron there, and some of them are in this dry scrub. And this is an important choice that individual reed warblers have to make, because if you look at the abundance of food in these habitats, in wetland and in dry scrub, food is much more scarce in the dry scrub. And there's variation within years, there's variation between years, but wetlands are consistently full of food. Dry scrub is a habitat where birds have a high starvation risk. So how do reed warblers survive overwinter in dry scrub, and why should they decide to do that at all? Relates to this idea of feeding strategies and body mass regulation. So by catching and weighing samples of birds in the wet habitat and the dry scrub and looking at their body mass, we're able to see that in wet habitat, reed warblers are skinny. In fact, they're quite close to their lean body mass. They're just not storing fat. Whereas in the dry habitat, where starvation risk is higher because food is scarce, just like the storm petrels, they've got this strategic buffer of extra body reserves in case they have a period of low food availability. So although food is scarce, when they do find food, they eat it all and build up this buffer. So this then might be part of the explanation why sedge warblers are so driven in their population level by Sahel drought, whereas reed warblers are much more independent of that, because in drought years they could move into dry scrub and still survive, whereas sedge warblers with their specialist diet, they are wet habitat specialists and much more prone to drought. So these are behavioural decisions, of course. Climate affects food availability. There's a whole suite of behavioural changes then that impact on breeding behaviour, breeding productivity, impact on overwinter survival strategy and how well they survive, and how many birds then are coming back and recruiting, providing offspring for the next generation. So that then influences population growth rate, which for reed warblers is actually quite a happy story at the moment. Quite what happens as climate warms and warms and warms, presumably food won't just go up and up and up. As food then goes down, we're seeing this kind of mechanism able to operate in reverse. And in drought years in the Sahel, for example, clearly these climate fluctuations have a massive impact. So just very briefly mention the last case study, which is the northern wheatear. The questions are exactly analogous to the reed warbler situation. So how does climate affect bird food and the timing of bird food? And how does changing food supply affect all these different behaviours? Wheatears are chosen because they have one of the longest sustained transoceanic flight of any migratory songbird. And so it's an extreme example, if you like. So Adam's work included the supplementary feeding, remote weighing, and so on. And you might think, well, this would just have the same effect on wheatears as on reed warblers, but actually there are important behavioural differences between species. So whereas reed warblers with food in their territory will give that food to the chicks, parent wheatears don't do that, they just eat it themselves. And so actually food availability has very little effect on the success of chick production from any individual brood, but it does allow the parents to lay eggs earlier every year because they're not dependent on temperature-driven reed growth. They nest in dry stone walls that are even there in cold years. By nesting earlier, they can have an extra brood. So if they fed, they can nest early and fit in a second brood and produce yet more chicks. And there's also an interesting behaviour-driven sex difference. So females are constrained to sit on the eggs, raise the chicks. Males aren't, and they can be polygynous. So they can have simultaneously another wife down the road who they're also producing chicks with. And so males are more affected in their breeding productivity than females by food supply. But on average, fed birds have higher breeding productivity. They also have substantially higher annual survival as well after they've left Shetland, and that is the case for both adults. Fledglings that have feeders in their territory after they fledge, but because their parents aren't giving the nestlings extra food, there's no effective feeding on the nestlings themselves. So just like with the reed warblers, climate warming increases food availability in these moorland habitats. There's a whole suite of behavioural change which leads to differences in breeding productivity, annual survival, and this drives population growth rate to the extent that in unfed territories, the Shetland population is contracting. It's got a small growth rate, but the fed territories are an expanding population. So you can measure these effects at the population level. So these case studies, to sum up, show how climate can affect food supply, and food supply is such a critical thing for these small birds with high metabolic rates, that this has knock-on consequences for a whole set of different behaviours. Although we think of migration as a behaviour, actually migration itself is a whole suite of different behaviours that affect survival, breeding productivity, and population change. But the important message here is that mechanisms are important. It's okay to measure population change, it's really important to measure population change, but behaviour actually gives some important insights into why those populations are changing in the first place. So the next steps involve trying to make this link between changing environment, behaviour, evolution, and demographic processes like breeding productivity feeding through to the population change. And in all of this, of course, understanding behavioural mechanisms is what we're looking at. Okay, that's it. Thank you very much.
Thank you very much, Rob. That was absolutely fascinating. Fantastic. Several steps of work there. We've gone slightly over time, so I won't take any questions. We now have